Myself, Mrs. Charushila Vijay Rane, I will be discussing the practical related to sampling theorem, which comes under the subject digital signal processing for the third year ENTC uh, students from semester 1. The aim of the experiment is write a program to verify the sampling theorem and aliasing effects with various sampling frequencies. Basically, the signals are categorized in two uh, types. First is analog signal and discrete signal. Analog signals are continuous in time. That means for each and every time instant, amplitude is indicated. But in case of discrete signal, the amplitudes are mentioned or specified for discrete values of time only. So to get the discrete version of signal from analog signal, we have to extract the samples from the continuous signal. So for that purpose, sampling procedure is required. In digital signal processing, the signal to be transmitted must be in discrete form only. Whatever are the practically available systems, these are digital systems. That means the input which we have to apply for these systems must be in form of digital. Analog signal directly cannot be applied. So before applying as an input to these systems, analog signal has to be converted in digital form. For that purpose, sampling process is required. While using the sampling process practically, the sampling rate should be properly selected. The sampling process should satisfy the following requirement. It should be possible to reconstruct the original signal from its sampled version. Means the number of samples available in the sampled version must be sufficient enough to reconstruct the original signal exactly. Sampling theorem. In order to represent the original signal successfully or faithfully, it is necessary to take as many samples as possible. Higher the number of samples, closer is the representation. The number of samples depends on the sampling rate selected and the maximum frequency contains of the signal which is to be transmitted or which we are trying to convert in discrete form. Nyquist criteria decides the sampling rate, or Nyquist criteria states the required sampling rate. A continuous time signal x of t can be completely represented in its sampled form and recovered back from its sampled form if the sampling frequency is greater than or equal to twice of the highest frequency content of that signal. That means sampling frequency fx has to be fs has to be greater than or equal to twice of the maximum frequency contains of the input signal. So what is aliasing? And that is also called as fold-over error. If the analog signal to be sampled is not strictly band limited, and if we are selecting sampling frequency which is less than the Nyquist criteria, that is which is less than twice the input frequency, an error called aliasing or fold-over error is observed. This distortion occurs due to the overlapping of adjacent spectrums in the sampled signal. And due to this overlapping, high frequencies are reflected into the low frequencies. And this phenomenon is called as aliasing. Due to aliasing, some of the information contained in the original signal is lost in the process of sampling. In this figure, the first figure indicates the spectrum of original signal. Second and third figure indicates the spectrum of sampled signal. In the second figure, we can see that the sampling frequency is less than the twice of the maximum frequency contents. And in the third figure, sampling frequency is greater than the twice of the maximum frequency contents. So since the Nyquist criteria is not satisfied in this figure number 2, we can observe the overlapping of adjacent spectrums, and that is called as the aliasing. But in the third case, when the sampling frequency is selected properly as per the Nyquist criteria, the spectrums are separated with some gap and there will not be any aliasing effect. So aliasing can be prevented by certain ways. First thing is that analog signal uh, must be passed through the band limiting filter before applying the sampling procedure. The sampling frequency is always selected greater than twice of the input frequency contains. Due to this, even though analog signal is not strictly band limited, the spectrum will not overlap. Guard band is provided between the adjacent spectrums. This way, aliasing can be prevented. Now the same thing, same theorem, we will verify by using the MATLAB software. So for that purpose, we will use the MATLAB 2020 software online. For that purpose, you have to type MATLAB online in your Google search window. After selecting the MATLAB online related link, we will get one option, start using MATLAB online. And if we are selecting that option, we will get this particular window. Here we can execute our program. Okay. Sampling theorem related code is shown over here. In every program, as a first line, we will always add a comment which is specifying the title of our practical to verify the sampling theorem and aliasing effect with various sampling frequencies. Clear all, close all, and CLC. These three commands also commonly we are applying in all the MATLAB programs. So clear all command will clear all the variables declared in the program. Close all will close all the figure windows, those are opened already. And CLC will clear the command window. Means because of previous execution, if there are certain contents in the command window at command prompt, this all the contents will be cleared by the CLC instruction. Then in the t variable, certain values are generated in the range 0 to tf. Tf range is given as 0.05. That means because of this instruction at line number 7, these are the line numbers mentioned in the MATLAB software. So at line number 7, the certain values are generated for variable t starting from 0 up to tf, that is 0.05 by the step size equal to the second figure given in the instruction. Then whatever is the original signal we are going to generate. So to generate that signal, the input frequency is accepted through keyboard from user by using the instruction input. So input instruction will display the message, enter the analog frequency F. And as a response to this message, user will enter some frequency value and that value will be stored in the variable F. Then based on that F value, the cosine waveform is generated in the next line of instruction. And that signal is stored in the variable X of t. So now this is the original signal and that we are going to sample at certain sampling rates, sampling frequencies. So while selecting the sampling frequencies, three different categories we will select. First one, we will try the undersampling. That means sampling frequency is selected less than twice of the F max. Then in second case, we will select the sampling frequency exactly equal to Nyquist rate. And in third case, we will select sampling frequency greater than the specified by Nyquist rate. So here in the first part, one signal cosine waveform is generated. Then first sampling frequency is given as 1.3 times of the original frequency of the signal. So this is the undersampling. Then the related time variable n1 is also generated. Then corresponding signal x of n, which is a sampled version with the frequency fs1 is stored in the xn variable. Now this signal, which is undersampled, is plotted in this section by using the plot instruction. In the second case, we will be selecting the sampling frequency, which is exactly equal to double of the frequency of original signal. And the respective sampled signal is plotted in the second section of figure window. And the title is given as Nyquist plot. X label, Y label is also allotted to the waveform displayed. As a third case, we are selecting a sampling frequency which is 10 times of the maximum frequency content of the original signal, which is far beyond the Nyquist rate. And the corresponding sampled signal is plotted in the third section of the figure window, and the title is given as oversampling plot. So now we will see the execution of this particular code. Because of this line number 8 instruction, the input is asked from the user, enter the analog frequency f and giving the frequency value equal to 50 and press enter so that the code will get executed and the corresponding result will be getting displayed in this figure window. Since I want to observe three waveforms parallelly, first one is undersampled waveform, second is sampling rate selected as Nyquist rate, and third case sampling rate is more than the Nyquist rate. So as we are observing three different waveforms in single window for comparison purpose, we have to split the figure window in three sections. That's why the subplot instruction is used with the parameter 3, 1, means 3 number of rows we need and single column we need. So this way 3 subsections are generated, and out of these 3 subsections, if I am using the first section, at that time I should mention in the instruction itself which subsection we are going to use. For example, to plot the sampled signal, we have selected the subsection 1. So that 1 is a third parameter provided for the subplot instruction. Similarly, we can see here the subplot instruction, the third parameter is given as 2. That means second subsection of the figure window is going to be used. So you can see here in the first subsection, in the first section, we are going to plot two waveforms, xt and xn. Xt is the original signal with given frequency, and xn is the sampled version of that with sampling frequency which is less than the Nyquist rate. So corresponding waveform we can observe here. The original signal is plotted in blue color because of this B parameter mentioned, and the sampled signal is plotted in the red color. So these are the sampled points because of this specified sampling rate. And if we are joining these sampled points, then whatever is the resultant signal is not able to reconstruct the original signal perfectly because the sampling frequency selected is less than the Nyquist rate. In the second plot, we can see that in the second section, we are again plotting two waveforms. First is the original signal xt, and the second signal is sampled signal with sampling frequency is equal to Nyquist rate, and that is plotted in red color. So because of that sampling rate, whatever the sample points we are getting, and if we are joining all the points in continuous way, then we can see that the original signal and the sampled version of the signal are closely related to each other. In the third case, if the sampling frequency or the sampling frequency is selected greater than the Nyquist rate, and if you are observing the sampled version of the signal, we can observe here that original signal and the sampled version of the signal are exactly mapping with each other, exactly matching with each other. So this way we can conclude that While sampling the signal, if uh, if the sampling frequency is selected at least equal to Nyquist rate, then the reconstruction of original signal is possible. If the number of samples are increasing, the reconstruction will be more and more better. But because of undersampling, the reconstruction of the signal is not at all possible. Thank you.